Here's number 4 from the Chapter 5 AP packet. The volume of a spherical hot air balloon expands as the air inside the balloon is heated. One of the few things as we do more and more problems is as soon as you realize I am dealing with some sort of geometric shape, related rates is most likely going to be a factor. The radius of the balloon in feet is modeled by a twice differentiable function, where t is in minutes. For the time interval from 0 to 12, the graph of r is concave down. Again, another piece of information. It's not just thrown randomly. It's really, really important that we understand that. The table below gives selected values of the rate of change r prime. That's just good to know. And then the radius of the balloon is 10 feet when t equals 5, a point given in time. The volume of a sphere is given by the formula. Estimate the radius of the balloon when t is 5.4 using a tangent line approximation at t equals 5. A tangent line approximation at t equals 5 means we want the equation of the line. Y minus y1 equals m times x minus x1, where in this case y is our radius and x is our time. So we need a point and a slope. So we need to know what is the radius at t equals 5 and what is the slope of the radius function, so r prime at 5. R of 5 is the radius of the balloon at time t equals 5, and that's why they provided it up here. It's 10. R prime of 5 would be given from the table. This is the graph of r prime. Here's where we get r prime of 5. The equation of the line would therefore be y minus 10 equals 2, x minus 5. Once we found this equation of the line, now we can use it to find what the radius would be at t equals 5.4. Y minus 10 equals 2 times 5.4 minus 5. Clean it all up, I get y equals 10.8. Is this estimate greater than or less than? Anytime we talk about under approximation or over approximation, we talk about a feature of the graph. Like, for example, is the graph increasing, the graph decreasing, concave up, concave down. When it comes to tangent line approximations, I care about the concavity. Since r is concave down, any tangent line drawn to it will always over approximate. So we want to say, since r is concave down, 10.8 feet will be an over approximation of r of 5.4, the true value. Both pieces need to be in this sentence. R is concave down because, or since r is concave down, therefore we will know 10.8 feet will be an over approximation. Part B, find the rate of change of the volume. That tells me it's a related rates problem. So I know volume equals 4/3 pi r cubed, and I'm going to need to take the derivative of this with respect to time. It even tells me with respect to time. Not always is that provided. So the derivative is dv dt equals, then it becomes 4 pi r squared dr dt. If I input all the values I know, for example, I know the radius at time t equals 5 is 10, and I know that dr dt is the same thing as r prime, then I have 4 pi 10 squared, and then r prime, it's actually up here still, it's 2. If I simplify this, I get 800 pi, indicate the units of measurement. This is why I really enjoy having dv dt right there. Volume is measured in cubic feet. Time is measured in minutes. Using a right Riemann sum with 5 subintervals, indicated by the data in the table, approximate r prime of t dt from 0 to 12. Using correct units, explain the meaning in terms of the radius of the balloon. R prime is the rate of change of the radius of the balloon. This is almost like looking at velocity. If I was integrating velocity, I get displacement. So it's telling me the displacement of the radius, how much the radius grew or shrunk. So using 5 subintervals, now they're not equally sized subintervals. It even mentioned, well, it didn't mention it specifically, but it said 5 subintervals. Since it doesn't tell you equal size subintervals, when I go back to this table, I can see the first rectangle, second, third, fourth, fifth. These two are 2 apart. These two are 3 apart. These two are back to 2. These next two are 4. And these last ones are 1. So I will multiply the width, which is the numbers I wrote at the top, times the, and I believe it said, a right Riemann sum. So this value, and this value, and this value, and this value, and this value. So let me write that out. 2 times 4 plus 3 times 2 plus 2 times 1.2, 4 times 0.6, and 1 times 0.5. This comes out to be 19.3. Using correct units, explain the meaning. Well, we just said it was a displacement, so that means this must also be in feet because I'm integrating a rate. The balloon radius grew by 19.3 feet, and then don't forget the time, during t equals 0 minutes to t equals 12 minutes. Lastly, is your approximation part C greater than or less than the integral? Give a reason for your answer. Remember to not make any assumptions, but use the facts that are given. So the reason I say that is because a lot of people are going to look at the table and just assume since all of these numbers are decreasing, well, that must mean r prime is decreasing. It doesn't go that far. We actually have to know more than that because, unfortunately, I don't know that at t equals 1, this graph doesn't actually go up to 6. So I need to go back to something else I know. Is there any proof of increasing or decreasing, or maybe concave up or concave down? Since I know r is concave down from the directions, that leads me to know, since r is concave down, r prime is decreasing. Since r prime is decreasing, then and it was a right Riemann sum, so a right Riemann sum will be an, now I gotta double check again, r prime is decreasing, and I have a right Riemann sum, it will be an under approximation.